Taught me that in physics.
Okay. Starts 12 of us, or 13, whatever. No, okay, never mind.
We should just go out to eat or something like that. Just forget everybody else.
Okay. Interesting idea. Yes, but I'm so sure that on the last day of class, everyone will show up because there'll be cake. No. Okay. All right, so continuing with
I am quite hungry.
Green's Theorem.
Sushi? That's raw.
All right, so, and actually this is a chance to clean up some things after the last couple of classes. So, the situation we have some two-dimensional region contained in a closed curve C, oriented counterclockwise. And as usual, C is represented by parametric equations, RT, that contain your x and y components only, there's no z here. T is between A and B. And then we have some region D that's enclosed. Bless you. And I'm going to draw this like using a dotted line. Holes in the region. So like if I call this curve C prime, and this will be oriented clockwise, so that if you have your little stick figure on any part of this boundary, this part or this part, and are walking along it, that the interior of a region D is on their left. So I'm going to refer to this as an optional hole, just so you know how broadly Green's theorem applies. And this has to do with the example that I did at the end of last class. So some notation that's going to be used throughout the rest of the chapter is this symbol. It's the same symbol that's used with partial derivatives, but when it's put in front of some region like this D here, this is used to refer to the boundary of D. Now, I have no idea why it was decided and accepted to use the same symbol to refer to partial derivatives and a boundary of a region. Must have been something where these were arrived at independently, and they saw a conflict. Like, oh, what are we going to do? Too late to change now.
We're going to have to start using rooms if we keep running out of variables.
Yeah, absolutely. So, okay. And in this case, the boundary of this region D would refer to C, and if there are any holes, it would be their union. Okay. All right. Now, so what Green's theorem says is that the double integral, that if we have a vector field F that has components P and Q that are functions of x and y, then the double integral over the interior D of dq dx minus dp dy is equal to the line integral over the boundary of D, which in this case would include, the outer boundary, this closed curve C, and also if there are any holes, you would include those too. So line integral p dx plus q dy, which is also written as the line integral of this vector field that I've already covered how to do. So if a boundary consists of more than one piece, like it did in the example in the last class, you would just integrate over each piece separately, and you would add the results together. And it's required that the boundary of D positively oriented. And this is a rule that I give that the inside is on the left. But what that means in counterclockwise or clockwise terms is the outer boundary is counterclockwise, as I've drawn here. And if there are any holes, you must integrate over them using a clockwise orientation. Now, so whatever parametric equations you're using for each of these pieces, and you can use what's convenient, but if it's a wrong orientation, then you have to remember that you reverse the sign. Okay. So the rule of thumb that I gave last time, that any line integral of a vector field, if you reverse the orientation, that's fine. You can do that as long as you remember to reverse the sign. Okay. So that's basically recaps what I went over last time. Now, a couple other points that I need to make before diving into examples. And I'll be using examples from the homework that's on this section. Okay. First, the integral, okay, so okay, actually, I'll do it this way. The line integral over the boundary, so the outer boundary and any holes, is equal to 0 if a vector field F is conservative in all of the interior. Now, the example from last time, I had its curves encircling the origin. The vector field F was not conservative at the origin, so that's why I had to cut out a hole. Okay. If I have a region with a hole, like this one, now the way Green's theorem is normally described, and the way I described it last time, is you just have some region that doesn't have any holes in it, and you are integrating vector field line integral over the boundary, and you can relate that to an integral over the interior. But the reason why it applies to regions of holes is I could put in a fake boundary here, and now I have two regions. I'll call this D1 and D2, and I can treat each of these as regions that are called simply connected, meaning they have no holes. So I could have this boundary for D2 oriented counterclockwise. Whoops. Okay. And then for this boundary, I'm also orienting it counterclockwise. But what that's going to mean is, as I go down this line, these line segments, they're going to be going the other way. And what happens is, the line integrals over these portions, what's going to happen to them if I integrate over them in opposite directions and then add them together?
Cancel.
They're going to cancel. Because when you change the orientation, that changes the sign. But everything's added together. So that's why the line integral over the boundary of D of my vector field, whatever it may be, is equal to line integral over a boundary of D1 plus the line integral over a boundary of D2. That if there are any shared boundaries as you paste these regions together, those line integrals will cancel. So that's really why I can state Green's theorem or prove it if I wanted to for just a non-whole region. And then here's how it generalizes to regions that do have holes. Okay. Now, what you're going to see in the homework is there's another way of stating Green's theorem that is entirely consistent with the first way, but I don't want you to get thrown off guard when you get to the homework. So really it's just a slight notation change.
Is that the homework that's due next week that you're referring to?
No, it's the one after that. Okay, so what we have is integral over the interior of d q dx plus p dy. Okay, I'll make sure I get this. Okay, yeah. Equal to the line integral over the boundary, which in most cases will just be a single closed curve, of q dy minus p dx. Or we might have like f and g here. It depends on the notation of a problem. Now, the only difference between this version and the other version is that p gets changed to minus p. Just so there's a plus sign in here. Now, what happens here is when you describe it like this, the meaning of this integral is the circulation of a vector field F, which has components QP around the boundary of D. So that's just the term that's given to this. So this is for a different application than the previous application I gave for line integrals, which was work done by moving an object along the curve. So the way the theorem works is still the same, and this is the notation change, and also you end up having the components of your vector field switched. But this statement is equivalent to the other one, as long as you keep in mind that you have p in one case and minus p in the other. So the way the theorem would work is still exactly the same. Again, just be consistent with your notation. All right. Now, there's one important application of Green's theorem that works well with this form that I want to make you aware of, and this also comes up on the homework. So, suppose P and Q, and I'm going to stick with the form that I just wrote for this just because that's what they stick with in the homework. And this is what happens when I write my notes based on one textbook and the department switches textbooks. Suppose they're chosen so that the integrand in Green's theorem, dq dx plus dp dy, is equal to 1. And there are many ways to choose that, and we'll pick one in a moment. Then this, and okay, we'll also, just for simplicity, we're going to assume no holes. So we have some region in the plane D, and the boundary is just some closed curve C with the correct orientation. All right. So then, the circulation of F around the curve, which is the same as Q dy minus P dx, as I wrote the second form of Green's theorem there. But by Green's theorem, that is equal to the double integral over the interior of dq dx plus dp dy. But now, if we've chosen this so it's equal to 1, so all we have is the double integral of 1. Now, what does this integral mean? What's its interpretation? What do you get when you integrate 1?
You just get that variable.
Well, that's the antiderivative, but geometrically, this is a big topic of last chapter that you had your test on. What? That's in 3 dimensions. Area. Yeah. So integral of 1, single integral gives you length. Double integral is area. Triple integral gives you volume. So this is the abbreviated A of D, but that just means the area of D. So, so we have a way of computing the area of any region in the plane, because by Green's theorem, you can backtrack up to here and just evaluate this. So, does anyone think of a way to choose Q and P? Think really simple things, simple functions, that would give you this, and there's more than one right answer.
Is this taking into consideration like a hole in the area? In
Oh,
the object.
Okay, well, for now, for simplicity, we're considering the no holes case, although what I'm describing can be used for areas or regions with holes, but you just have to evaluate an integral like this over the outer boundary and the holes. But if you want these partial derivatives to be constant, then what should Q and P themselves be?
Constant.
Just variable, like x. I'm sorry.
Yes. So, okay, so to choose Q and P, all right, so one way is you could choose Q to be equal to x. So then partial Q with respect to x would be 1. And therefore, you might as well choose P to be 0. What would be another way?
The
Could you-
opposite?
Yeah, what would that be?
P would be equal to X.
No,
Y.
Y.
And
And
Q
Q is
equal to
equal to
0.
0. Okay, can anyone think of a way that would have both Q and P equal to something non-zero, but still similar idea?
Then negate of each other?
Yeah, take half. You basically average the two. So Q is equal to X over 2. P is equal to Y over 2. Doesn't really matter which one you use, but so if I go with this one, what I can give you from this is a surprisingly simple formula for the area of any polygon. And you know formulas for the areas of certain polygons, certainly triangles, rectangles, parallelograms, things like that. And then you can look up formulas, the ones you may never been taught or maybe don't remember, like regular polygons. The polygons where all sides have the same length and the same interior angles. There are formulas for that. But for just for general polygon, whatever shape it has, you wouldn't have been taught a formula for that. but now I can give you one. So if you're given, some polygon, no matter how irregular shape it has, and you were given, okay, that should be a straight line. Okay, not many of these are straight, but you get the idea. And you label the vertices so that you're going around clockwise. So you keep going around and around and around until, let's say there are n vertices, this is the last one. So you keep going around this way. So you have the x and y coordinates of the vertices. So what you can do is, I'm going to label these sides. I'll call this C1, C2, C3, and so forth, all the way down to the last one that goes from point N back to point 1 to close the loop. And I'll call that Cn. So I can say that the interior is D. So the area of D, by Green's theorem, is the line integral over the entire boundary C, which is the union of all n sides of 1. So 1/2, and we have x dy minus y dx. And I can break that up into a sum over each piece. And each of these pieces is very easy to parameterize because it's just a line segment. So each piece I can parameterize by x is just t, where t goes from, let's see, what I'll do is, I'll show you the first one, just so so we go from x1 to x2. Now here we're assuming that the piece is not vertical. If it was vertical, then that would be an exceptional case, but you'll get the idea from this. And then y is just mx plus b, or mt plus b, because x and t are the same. And it's just a matter of getting the equation for both points, equation of a line from 2 points. So m is just the slope of that segment, and then your y-intercept is just that. So now we have parametric equations, and then dx dt is just going to be 1, and dy dt is just going to be m. So all that works out nicely. So what we have is the line integral over C1 of, so we have 1/2 x dy minus y dx, and the integrals are very simple in this case. So it would be the integral from x1 to x2, and then we'd have, so x is equal to t, so I'll fill in t. Then dy is m, minus y, which is mt plus b, dx, which is 1 dt. So all you'd have to do is work this out. But it gets even easier, because what happens next? What can I simplify here?
The Tn minus mt.
Yeah, those cancel, so it's 1/2 the integral of minus b. So after you work all that out, what you get is 1/2, and you have x1 y2 minus x2 y1. That's it. So that gives you line integral over that one piece. So now you just add all of these together. So here's the formula for the area of any polygon where the vertices are ordered in this counterclockwise manner. So it's 1/2, and you have n terms. So you have this first one, x1 y2 minus x2 y1. Then you do the same thing for the next piece. x2, y3 minus x3, y2. Always dealing with consecutive vertices. And then you keep going all the way down to x n minus 1 xn minus xn.
Would it be YN?
Yeah, that should be a y. X n minus 1 yn minus xn yn minus 1, because it's always xy products. And then you hit the last vertex, but then you have to loop back around to the first one. So you finish with xny1 minus x1 yn. That's it. So this is the area of an n-sided polygon. So if you have the coordinates of vertices, it's a piece of cake. And Green's theorem gives us that. So maybe some problems in the homework that that relate to this. Although I found it amusing that one of the problems asks for an area of a shape, and to figure it out, doing something like this, having a circulation integral. But the shape is so simple that you can figure out the area by other means, and it's not going to know. So I guess that's a freebie from me. Okay, not that I had to tell you, but whatever. Yeah, but keep in mind, if I ask a similar thing on a test, I can ask you to show your work. So keep that in mind. Okay, so any questions about that derivation? Mark, many people absent. All right. Now, I want to make sure that we make time for any questions anyone has on the current homework. Anybody? Keep in mind that this is not a way to get out of class early because I do have more stuff. That incentivizes everyone.
Can we do number 7?
7. Okay.
That's section 15.2.
Yeah. Okay. Okay, 15.2. Oh, it won't let me preview, because I also had 15.4 up for Green's theorem examples, but it won't let me do that. Or it won't let me have two up at the same time. So this is number 7. Okay. I didn't realize that orientated was a word. You'd think it would be oriented, but whatever. Okay, so this is... Alright, so you are given this vector field, components P and Q, what's my notation, not theirs, and you have this factor out front, x squared plus y squared to the 3/2, and your components are x and y. Okay, and then the curve, okay, has these components 2t squared and 3t squared. And t goes from 1 to 3. Okay, so random. Okay. Now, yes, the way they write the line integral that they want is a little odd, but I assume is this about the setup of it, or whoever has the question?
I mean, I'm not honestly sure what I'm getting wrong. I feel
Okay.
like I'm setting it up right. And it
Okay.
may be the algebra, but I'm not.
Okay, well, this will be an opportunity to confirm that. And this is also how I write f dot dr, but so what's happening is you would have the integral from 1 to 3 dt, and well, actually, before I get to that point, so you have p dx plus q dy, and let's get our derivatives lined up. So x is 2t squared, y is 3t squared. So what are our derivatives?
4t and 60.
Yeah. Okay. So 1 to 3, and we're going to have this factor of multiplying everything. So we're going to have x, which is 2t squared plus 3t squared, all raised to the 3 halves. Well, at least that'll simplify by the time we throw everything in. And then you have p, so this is our components, p and q. So, so we have our x component of our vector field here, which in this case is just x. So we're going to have 2t squared times dx, which is 4t. So that's p dx plus the y component of our vector field, which in this case is just y, so that's 3t squared. And then you have
60.
dy, which is 6t, all dt. Okay. All right, well, questions to this point about the setup? A whole lot, yeah, actually a whole lot's going to simplify. Because we have 8 plus 18 is, so this condenses to 26 t cubed. And then what we have down here on the inside is 4t to the 4th plus 9t to the 4th, so 13t to the 4th. But what happens when we raise all of that to the 3/2 power? Anyone? What are your laws of exponents?
Just did it.
Well, no, I mean, the 2 is going to cancel out. 1 and
This
2.
is
Well, you do get a t to the 6.
6, but
And then what else were you saying?
I don't know, that was what
Yeah.
I was
Okay.
trying to relay.
Okay. All right. So we have. All right. So we have 26t cubed up top, and then we have 13 to the 3/2. That's not going to work out nicely. And then t to the 6 dt, and then, of course, you can condense this, and you're going to get a constant times t to the -3.
does it end up being like 13 and the square root of 13? Is it something like that?
You can write it that way, yeah. Yeah, just because you could break it up as 13 to the 1st times 13 to the 1/2. Okay. At least this one you can just power rule it. It's frequent to have mistakes dealing with negative exponents, so I don't know if that's what happened in your case, but is the setup at least consistent with what you have? Or?
Yeah, I think it was just like I was messing that up. Right?
Okay. Any other questions on this one or another one on this assignment? All right. Okay. Now, if anyone thinks of another one before time is up, of course you can chime in with that. Now, I'm going to navigate to the homework for Green's theorem. Okay. find an interesting one. Okay. I try not to be that professor who just only picks up the easy example in the section and does that and leaves you adrift. But the trouble is in this class, examples take long. In fact, there's been some deliberation for the future. Do we want to make this class a 4-credit-hour class like they do with Physics 201? And I'm sure that if we went to administration with that, they'd be like, please don't. But, okay. So this is, whoops, 15.4 homework, number 3. Okay, so the region that you're evaluating line integral for, but described in words here, is upper half of a unit circle. So this is your origin. This is a segment from -1 to 1. So, and this is oriented clockwise, which flies in the face of Green's theorem. Green's theorem, we always say the boundary must be oriented counterclockwise. But that's no problem. All you do is just go ahead and work out the line integral and just remember to negate it at the very end. So use whatever parameterization is convenient. So this has radius 1. And the vector field that's given, okay, so you have to evaluate f dy minus g dx. And f and g are given to be 9x squared and 9y squared. Okay. Now, you can use whatever, I've written Green's theorem 2 different ways. You can think of it however you want. So for instance, you could think of this as being your p, and that would be your q. Whatever's in front of the dx, sign included, is your p. Whatever's in front of the dy, you can think of that as your q. And based on how I normally write Green's theorem, this would be dq dx minus dp dy. But that would be same as the, okay, so this would be, q is f. So fx, and then p is equal to minus g. So we'd have plus gy. Okay. So now I can fill in what this is, take the derivatives. So fx, so I differentiate this with respect to x, so that'd be 18x. And then for dg dy, that'll be 18y. Okay. So by Green's theorem, this is the integral that you need to evaluate that would happen to give you this, as long as we negate at the very end, because it said clockwise orientation. Okay, so actually, so for your notes, if a problem states that, okay, so that's one extra step. Okay. Now, there's a couple ways you can handle this integral. If you stick with x and y coordinates, you can integrate from -1 to 1 in x, and then from 0 to square root of 1 minus x squared. So you can always do it that way. What's another way to work out this integral? Keeping in mind this domain now, because this is our interior D, C is the boundary. So what would be likely a better way to handle an integral like this? that you also have to do in the last test. What?
I don't remember the name of
Okay. Well, hopefully somebody will.
Polar coordinates.
Polar coordinates, yeah. So in polar coordinates, okay. You can't afford to be dumping that knowledge after you spewed it all over your test. And some did not spew enough. Or at least take it all in again before a final. So we do this in polar coordinates. We have variables r and theta. Hopefully this rings a bell. It was so many weeks ago. All right, so r is distance from the origin. Yes. And what would theta be for the top half?
it. 0 to pi.
0 to pi. Okay. So those would be limits. This is nice because we have constant limits for both variables. So we have, okay, so 0 to pi in theta, 0 to 1 in r. And, well, I'll factor out the 18. So what happens here with the integrand? How do we write that?
R squared. Oh, no, R.
R,
R
And then R
squared.
again.
Plus R times.
well, there is going to be an r squared ultimately. But to go one step at a time, x is r
Cosine.
cosine theta.
Oh, okay.
Okay, and then r sine theta, so this is x, and this is y. And then, yeah, the extra factor of a Jacobian, the polar coordinates is r. And then you can go ahead and evaluate it from there. All right, so that's something you'll do when you get to that homework. Okay. All right. Now, any questions on the setup of that one?
Since our boundary goes clockwise in this,
Yeah.
and theta, I don't know, I guess I'm just struggling to see why it's 0 to pi, not pi to 0.
Oh, okay. What do you have to? Okay, there's two ways you can do this. Green's theorem has a built-in assumption that when you change the integral over a curve to an integral over the interior, that the curve is oriented counterclockwise. So you can either just go ahead and go with it and then negate your answer at the very end, where you're using, because the thing is, going from -1 to 1, if we just use the simplest parametric equations for that, that would be counterclockwise. And also the natural parameterization for the circle, like x is cosine theta, y is sine theta, also counterclockwise. Or, really the only way to, if you were not using Green's theorem at all, just evaluating this directly, you could either stick with those most convenient parametric equations that I described, and you still have to negate it, or you come up with different parametric equations that really do go around the curve clockwise, and then you don't have to negate it. So you decide which is easier.
Gotcha.
By negation, you just mean change signs.
In this case, yes. Yeah. Yeah. So the best thing to do is keep track of your orientation and use whichever parametric equations are the most convenient. Because yeah, you can always reverse orientation, but sometimes it's a pain. Okay. Your questions about this one? Anyone have any other 15.2 homework questions? Okay. All right. All right, I'll do a setup of one more, and then we'll stop. Also from the Green's theorem homework. Okay, so this is number 4. And we have, so we asked for line integral of a vector field over a curve C, where the curve C is the boundary of such that x goes from 0 to pi, y goes from 0 up to sine x. So what we have here is, so x going from 0 to pi, y is going to go like this, because sine is 0 at both points. So this is your region D. The curve C, with counterclockwise orientation, and the problem says that counterclockwise. And the vector field given is okay. So we have 4xy squared 5x cubed plus y. Okay. And okay. So now your limits would come straight from a description of a region. So we'd have 0 to pi in x, and then 0 to sine x dy. And so what happens is, the way they express the circulation line integral would call for, so if we label this, okay. Hold on a second. All right. All right. So we have this is your P, this is your Q. Then we'd have so QX minus PY. So these partial derivatives are what you fill in here. And then, so there's no need for a coordinate change in this case, like polar coordinates. It wouldn't really make sense for a region like this because that's not really part of a circle. Because that's y equals sine x. And I'm out of time, but you can fill it integrate into there and then do it like a normal double integral from the last chapter. Any questions about the setup? Okay, and hopefully I'll see you and the rest of your classmates on Friday. It's Friday, it's not very optimistic.